Right now, somewhere in this universe, there could be a planet where creatures with eyes, limbs, and brains are staring up at their own night sky, wondering if they're alone. And the wildest part? Based on everything we understand about biology, those creatures might not look as strange as you'd expect. They might look weirdly familiar. So why did evolution on a completely different world produce something that resembles us? And if these beings exist, where are they? And what would they actually do if they found us? Those aren't just fun hypotheticals. The answers could determine whether humanity thrives among the stars or never sees the threat coming. Let's start with something you probably haven't thought about: your body. Look at your hands for a second. You've got opposable thumbs that let you grip tools with ridiculous precision. You've got a digestive system that strips raw materials from food and rebuilds your cells with them. Your heart will beat roughly 2.5 billion times across your lifetime without you ever thinking about it. Every single part of you was sculpted over millions of years to do a specific job and to do it efficiently. That's a principle biologists call form follows function. The shape of an organism is dictated by what it needs to do to survive. And this principle doesn't just apply to humans, it applies to everything alive. When Charles Darwin sailed through the Galapagos Islands, he noticed finches on different islands had completely different beaks. The finches that ate hard seeds had thick, powerful beaks built for cracking. The ones that hunted insects in tight crevices had thin, delicate beaks designed for precision. Same bird family, different tools for different jobs. That observation became the foundation of evolutionary theory. Nature experiments constantly, and whatever works survives. Now here's the part that gets really interesting for the alien question. Nature doesn't just stumble onto a good idea once, it does it over and over again. The eye, for example, has evolved independently at least 40 separate times across the history of life on Earth. 40 different species that couldn't see gradually developed the ability to detect light, and they did it without copying each other's homework. Bats evolved wings completely separately from birds. Bats and dolphins both independently figured out echolocation to navigate in darkness. Koalas developed fingerprints that are nearly identical to human fingerprints, and were not remotely related. This phenomenon is called convergent evolution. When the same environmental pressure exists, like abundant light or the need to navigate without visibility, nature often lands on the same solution through completely different paths. And this has a massive implication for alien life. If a planet out there orbits a star similar to our Sun, with a similar atmosphere and a similar temperature range, the life that evolves there might solve the same problems the same way. Eyes would probably still be a good idea, limbs for moving across terrain, some kind of manipulator appendage for using tools, a centralized processing organ for decision-making. All of those features aren't random. They're responses to universal problems that any complex organism would face, which means those humanoid aliens in science fiction movies might not be as lazy a design choice as you thought. Convergent evolution suggests that something roughly our shape could genuinely show up on another world. Now, the environment would absolutely put its own stamp on things. On a planet with significantly lower gravity, organisms could grow much taller and more slender because lifting nutrients through a body or pumping fluids against gravity would cost far less energy. Flip that around, and on a high-gravity world, you'd expect stockier, denser creatures with reinforced skeletal structures, or possibly aquatic species, since water offsets the crushing weight. A planet further from its star would have less light, so eyes might be enormous. Or maybe those organisms would rely entirely on something like echolocation or sensing vibrations through the ground. Planets with extreme temperature swings could produce life that hibernates for long stretches, or organisms capable of shutting down almost entirely and rebooting later, similar to tardigrades surviving the vacuum of space. In every scenario, the same rule holds. Form follows function. The environment writes the blueprint, and evolution builds to spec. So convergent evolution tells us what aliens might look like. The next obvious question is whether any of them actually exist out there. And for that, we have a genuinely clever mathematical tool. In 1961, astronomer Frank Drake sat down at the first Search for Extraterrestrial Intelligence meeting and proposed a formula. It's called the Drake equation, and it attempts to estimate how many detectable civilizations might exist in our galaxy right now. The equation multiplies 7 factors together: the rate of star formation, the fraction of those stars with planets, the number of planets per system that could support life, the fraction where life actually develops, the fraction where that life becomes intelligent, the fraction that develops technology capable of sending signals into space, and finally, how long those civilizations survive. Some of these numbers we can estimate with decent confidence. Astronomers calculate that roughly 5 new stars form in the Milky Way each year. Thanks to the Kepler space telescope, we know that planets are extremely common, with nearly every star hosting at least one. The fraction of those planets sitting in the right zone for liquid water, with the right mix of elements, lands around 0.3%. Small, but across hundreds of billions of stars, the raw numbers are still staggering. Where it gets tricky is the biological variables. We only have one example of life arising anywhere, and that's us. Life appeared on Earth almost as soon as the planet cooled down enough to allow it, which might suggest it's nearly inevitable under the right conditions. On the other hand, all life on Earth traces back to a single origin event. One moment, chemistry became biology, and it apparently never happened again on this planet. So, is life a guaranteed outcome or a 1 in a million fluke? We genuinely do not know. Intelligence is an even harder call. Millions of species have existed on Earth, and exactly one developed the kind of complex technological civilization we're talking about. Octopuses solve puzzles and use tools, certain birds demonstrate impressive problem solving, but none of them are building radio telescopes. If you plug in pessimistic numbers, assuming life and intelligence are both extraordinarily rare, the equation spits out 0 civilizations in our galaxy. We are completely alone, floating through an empty cosmos. If you plug in optimistic numbers, assuming life is common and intelligence eventually follows, the result jumps to somewhere around 9 civilizations broadcasting right now. And if those civilizations manage to survive for billions of years, the number climbs into the millions. Same equation, wildly different results, depending entirely on assumptions nobody can verify yet. That uncertainty is either deeply unsettling or incredibly exciting, depending on how you look at it. If you're finding this helpful, hit subscribe. We cover space and science topics like this regularly. All right, so let's say alien civilizations do exist. That opens a question that honestly matters more than what they look like. What would they do when they find us? We can approach this by looking in the mirror first. Humans are the only technological civilization we can study, and our track record with first contact is not encouraging. When the Spanish conquistadors encountered the Aztec Empire, the technological gap between the two groups was enormous, and the results were devastating for the less advanced civilization. Throughout history, whenever two human cultures with different levels of technology have met, the more powerful group has almost always exploited or displaced the other. An alien civilization capable of reaching Earth would, by definition, be far more advanced than us. And if their biology was shaped by the same evolutionary pressures as ours, meaning competition for limited resources, survival of the fittest, expansion into new territory, then aggression is at least plausible. They didn't become a spacefaring species by being passive. Technology makes this scenario terrifying in a very specific way. You don't need an invasion fleet to destroy a planet. If you can accelerate a large asteroid to a significant fraction of the speed of light, the energy released on impact would sterilize an entire world. The target wouldn't even see it coming. Any species capable of interstellar travel would understand this physics. And that leads to one of the darkest proposed answers to why we haven't heard from anyone. It's called the dark forest theory. Imagine every civilization in the galaxy as a hunter walking through a pitch-black forest. You can't see the other hunters. You don't know if they're friendly or hostile. You know that if you reveal your position, someone might shoot first and ask questions never. Under those conditions, the only rational strategy is silence. The civilizations still alive are the ones that never announce themselves. The loud ones are already gone. There's a less dramatic possibility too: indifference. A civilization millions of years ahead of us might view humanity the way we view an anthill. They understand what we want perfectly. We have zero capacity to understand them. Communication would be pointless from their perspective. We might have some value as a curiosity, a biological specimen in some enormous cosmic nature preserve. And any good zookeeper knows that the best enclosures look exactly like the animal's natural habitat. If something is watching us, they might prefer that we never know it. Both of those options are pretty bleak. Fortunately, there's a third possibility, and it might actually be the most realistic one for advanced civilizations. Cooperation. Cooperation exists throughout nature. Wolf packs hunt together, protecting members of the group even at personal cost. Ant supercolonies spanning entire countries share resources across billions of individuals. Humans themselves wouldn't have built a single city without learning to collaborate. Nobody alive knows how to build a computer from scratch, but thousands of people collectively know how to mine the silicon, fabricate the chips, assemble the components, and write the software. Civilization itself is a cooperative project. And there's a compelling argument that as technology advances, cooperation becomes not just useful, but mandatory. The more powerful your weapons become, the more catastrophic conflict gets. At some point, a species either learns to resolve disputes without violence, or it destroys itself entirely. There's no middle ground when your weapons can crack planets. So advanced civilizations may have been forced into cooperation by sheer survival pressure. If that's the case, there could be an enormous galactic community out there, a network of species that figured out how to coexist. Maybe they don't talk to us because we haven't passed the test yet. Until we demonstrate that we can stop fighting each other, sharing advanced technology with us would be like handing a loaded weapon to a toddler. They might be waiting for us to grow up. Now, all of this assumes alien life exists in the first place. So let's go back to the very beginning and ask an even more fundamental question. How did life start on Earth? Because if we can understand that process, we can estimate how likely it is to happen elsewhere. About 4.5 billion years ago, Earth was a molten hellscape. The moon had just formed from a massive collision, the surface was covered in lava, and the atmosphere was a toxic mix that would kill any modern organism instantly. Oceans began forming around 4.4 billion years ago as the planet cooled. And here's the part that catches every scientist's attention. The earliest evidence of life appears potentially as early as 4.3 billion years ago. Almost the instant conditions allowed it, something started living. For something supposedly improbable, that timing is suspicious. Life requires three basic molecular building blocks: fatty acids, which form the membranes that create boundaries around individual cells; amino acids, which build the molecular machinery inside those cells, things like enzymes and structural proteins; and nucleotides, which store information in RNA and DNA. All three of these existed on early Earth, and all three have been found on asteroids drifting through our solar system. The raw ingredients weren't special, they were everywhere. Fatty acids do something remarkable in water. Because one end of the molecule attracts water and the other repels it, these molecules spontaneously arrange themselves into hollow spheres called liposomes. No designer needed, no complex process required, just physics and chemistry doing their thing. These liposomes can even divide on their own and speed up internal chemical reactions by concentrating molecules in a smaller space. RNA, the information carrier, can do something unexpected too. Short strands of RNA can catalyze chemical reactions, essentially kickstarting primitive chemistry without needing the complex enzymes that modern life depends on. And when random RNA sequences ended up inside those primitive fatty acid bubbles, some of them produced amino acid chains that happened to stabilize the membrane wall. The bubbles containing useful RNA survived longer and divided more successfully. That's selection pressure at the molecular level, evolution before anything was technically alive. The physicist Erwin Schrödinger pointed out something crucial about life and thermodynamics. Life appears to defy entropy, building incredible order from chaos, except it doesn't actually break any rules. When you include the surrounding environment, entropy increases overall. Life is just extraordinarily efficient at converting energy and accelerating that process. Pound for pound, a resting human generates about 6,000 times more power than the surface of the sun. Life doesn't fight physics. Life is what physics does when you give it enough energy and enough time. And early Earth was essentially a giant battery, The acidic ocean above and the alkaline, electron-rich mantle below created a massive chemical imbalance. Wherever the inside of the planet met the outside, at deep-sea hydrothermal vents, volcanic hot springs, gas-filled caves, that energy gradient could power the chemical reactions leading toward biology. One crucial detail: a new form of life emerging from scratch today is considered basically impossible because our atmosphere is now loaded with oxygen. Combine hydrogen with oxygen and you get an explosion, not a living cell. The window for abiogenesis closed billions of years ago on this planet. But that doesn't mean it hasn't opened somewhere else. So if life's ingredients are common and the process might be nearly inevitable under the right conditions, the question becomes, where should we look? This is where the Kepler space telescope changed everything. Kepler spent years staring at a fixed patch of sky near the constellation Cygnus, monitoring about 150,000 stars for tiny periodic dips in brightness. Those dips indicated a planet passing in front of its star. Before Kepler, we knew of only a handful of exoplanets, and they were mostly gas giants many times the size of Jupiter. After Kepler, the confirmed count exploded into thousands, with thousands more candidates still being verified. And remember, that was from observing just one small section of the sky. Kepler's successor, the TESS spacecraft, covers an area 400 times larger and is expected to find over 20,000 exoplanets during its mission. Out of those thousands of confirmed worlds, 16 are rocky planets sitting in the habitable zone of their stars, the distance where liquid water could theoretically pool on the surface. Water matters enormously for biology. It dissolves and transports nutrients, it provides a medium for biochemical reactions, and it makes up more than 60% of the human body. A planet without liquid water is a much harder place for life as we understand it to get started. Of those 16 candidates, several orbit so close to their stars that they're likely tidally locked, with one face permanently baking and the other permanently frozen while being bombarded by enormous amounts of radiation. When you filter for planets that are genuinely Earth-like in the ways that matter, the list narrows to about 4 strong candidates. That's not many from a sample of thousands. But here's the wider calculation. Using Kepler's data as a statistical sample, astronomers estimate that roughly 6.4 billion rocky planets may sit in habitable zones across the Milky Way alone. 6.4 billion chances for the right conditions. We can now study these worlds in ways that would have been science fiction 20 years ago. By analyzing the spectrum of starlight passing through an exoplanet's atmosphere, scientists can identify specific gases. Oxygen, water vapor, carbon dioxide, and methane each absorb light at particular wavelengths, leaving a chemical fingerprint. If a distant world shows an atmospheric spectrum similar to Earth's, it could mean habitable conditions. And if that spectrum contains molecules that only exist as byproducts of biological activity, like certain industrial pollutants or methane produced by living organisms, that could be a biosignature. Direct evidence that something is alive. The James Webb Space Telescope is already studying known exoplanets in this kind of detail, examining their atmospheres for exactly these chemical clues. Combined with TESS finding new worlds at an accelerating rate, the next decade of astronomy could produce one of the most significant discoveries in human history. Or it might confirm that we really are alone. That life on Earth was an unrepeatable accident, a one-time miracle of chemistry in an otherwise dead universe. Personally, the math makes that hard to believe. 6 billion potential homes in just our galaxy, ingredients that form spontaneously in water, a process that apparently got started on Earth almost immediately. Either the universe is spectacularly bad at making life and we hit a cosmic lottery, or the cosmos is teeming with organisms we haven't figured out how to detect yet. And there's something almost poetic about that uncertainty. On a clear night, far from any city lights, you can see thousands of stars with just your eyes, each one potentially hosting worlds where the same chemistry, the same physics, the same evolutionary logic is playing out right now. Creatures evolving eyes because light is plentiful, building tools because competition demands innovation, looking up at their own sky and wondering if anyone is looking back. We are either the only minds the universe has ever produced, or we are one voice in an enormous chorus that we haven't learned to hear yet. Either answer changes everything about what it means to be human. And right now, for the first time in history, we actually have the technology to start finding out. The silence from the sky isn't proof of absence. It might just mean we're still learning to listen.